Welcome once again on the dark side of space science. Today I would like to take you for a ride into the darkest depths of theoretical physics and expose some of the unpleasant secrets hidden below the deceptively smooth surface of mainstream theories. Although I still didn't finish dealing with the problem of constant light speed in relative motion, I decided that it might be a good idea to take a short break from the abstract aspects of unified relativity, like empty space or virtual dimension of time. In today's lesson, I want to deal with things which are much more visible and touchable. That means solid matter and physical forces associated with it. However, if you think that I will at last come back to plasma physics and interactions of electromagnetic fields in the solar system, you might be once again disappointed, as instead of MHD, I wish to speak about the curves of time-space, which we call as gravity. To be more specific, I want to discuss one of the biggest problems of standard model, which is the elusive dark matter, and look for a possible solution for the great amount of mass which is apparently missing in the observable universe. As most of you might know, scientists assumed the existence of dark matter after they noticed that things predicted by their models didn't match things which they observed. In order to get some valid results from their models, they had to add some completely invisible and untouchable kind of mass to the equation. According to official knowledge, baryonic matter, the one which we can observe, makes only 5% of the total mass in the universe, while dark matter makes around 27% of it. The rest of missing mass is known as dark energy, and is just as hypothetical, if not more, as dark matter, and remains far beyond our understanding. Up until today, and despite great efforts, dark matter and dark energy remain hidden in the dark, and nothing doesn't seem to change in the near future. Multiple attempts to find the invisible matter and billions invested in research didn't give us anything, not a single clue as for the missing 95% of mass in the universe. I won't even try to count how many times we've heard about a new revolutionary theory which might finally solve the problem of dark matter and dark energy. Negative mass, quantized inertia, WIMPs and machos, anapoles or axions from different dimensions, just to name a few. And yet, none of those revolutionary theories didn't turn out to be the right one. In year 2019, our understanding of dark matter is the same as 1930. That means known. And this is exactly why I would like to look at this problem from my non-professional point of view and propose my own solution, which appears to me as the simplest and most obvious one. In this particular case, we need to begin from asking the right question, which is, what should be done if values predicted by a theoretical model are different than values which we observe? According to the majority of professional physicists, the correct answer is, we should make up some virtual factors and add them to our models so the predicted values will match observed ones. However, amateurs like me might come out with a different answer, like, we should probably try to modify the theoretical model so the values which it predicts will match the observed ones. Sadly, I can only imagine the shocked face of scientists. Okay, I won't pretend that I'm the first one who figured out such solution. There were already some attempts to use a different model of gravity, like modified Newtonian dynamics, MOND, which is able to solve some of the inconsistencies between predictions and observations. However, it is also unable to deal with a big portion of phenomena observed in space, and was rejected a long time ago by the majority of scientific community. It seems, however, that there are still some physicists who are considering the possibility that the official model of gravity might be wrong. However, except the MOND, there were only few attempts to propose any possible alternative to solve the problem of missing mass in the universe. Theoretical physicists are more interested in making new theories than fixing the existing ones. Luckily, I'm not a professional physicist and I don't have a scientific career to risk. This is why I can do whatever the hell I want, without facing a possible banishment from the scientific community as a consequence of my controversial statements. So let's now look closer at the problem which many physicists consider as main evidence of the invisible dark matter. And here it is in its full glory. What is being presented on this animation is the rotational motion of a galaxy. On the left side we can see the result which is predicted by the theory, while on the right side we can see the rotational motion as it is being actually observed. It is pretty clear that further from the galaxy center, observed velocity of rotational motion is much faster than the one which is being predicted. Graphs on the bottom are called galaxy rotation curves and represent the distribution of rotational velocity in space. As you can see, velocity of stars doesn't decrease as it is predicted, but seems to maintain a constant value with the growing distance from the galaxy center. And since the official models are treating gravity as the only force that matters in the universe at macro scale, observed rotational motion can be theoretically explained by including additional invisible mass, a lot of it, in the outskirts of a galaxy. And this is exactly what was done. This virtual mass is now known as dark matter halo. Problem solved. Today, the existence of dark matter halos is considered as settled and undeniable. Without it, official models of galaxy formation wouldn't work at all, just like many other models of macroscale objects. And because up until now, no one didn't find any alternative solution, dark matter remains a crucial factor in the theoretical cosmology, despite the lack of any empirical evidences of its actual existence. Problem is that questioning dark matter is reserved only for those with authority in theoretical physics. Any common scientist who would try to deny the existence of dark matter is being quickly removed from the public view while his claims are being radicalized and ridiculed. And this is exactly why amateurs like me have the upper hand when it comes to radical claims regarding fields of physics which are still unknown to mainstream. And now I will use this advantage to show you that there still might be solutions which don't require any revolutionary and innovative theories, and that sometimes even a tiny detail can change everything. As I said many times before, I'm not a professional physicist, and maybe this is why, instead of solving sophisticated calculations and following the generally accepted trends, I've learned to trust in my non-physical intuition. And just with this intuition, I was able to find two possible solutions to the problem of galaxy rotation curves. They can be easily combined into a single model, capable to explain most of the observed examples used currently as proofs of supposed dark matter. Generally speaking, first of my solutions is mostly about fixing some issues in the mainstream model of gravity, while second is about adding an important and well-known mechanism to the equations. But to keep things clear, I will begin from the first part, which deals with gravitational fields. Let's start from discussing the model which is being used to calculate the rotational velocity of galaxies. Some of you might be aware that there are in fact two parallel theories which describe the gravity and gravitational fields of celestial bodies. To make things funny, both theories are partially excluding each other, and yet in standard model they are being combined into a single model. One of them is the Newton's law of universal gravitation, and second is the Einstein general relativity. First, let's look at Newton's formula for gravitational attraction, known as inverse square law. Here are all the details of this formula. Most of you probably learned about it in school, as it is one of the most basic laws of physics. But what is important for the subject which I want to discuss is to remember that for bodies which are spherical, we need to use the distance between their centers of mass. When it comes to Einstein and his general relativity, things are getting slightly more complicated. While according to Newton, gravity is just a physical force, Einstein's theory tells that the attraction between matter is in fact a result of space and time being curved by the presence of mass, which is in fact a kind of energy. Such a description of gravity is able to explain some phenomena which couldn't be explained by Newton's model, like gravitational lensing, gravitational waves, or the time dilation due to the presence of mass-energy distribution in space. Einstein's model was able as well to properly predict some behaviors of planet, but I won't go deeper into all the details. To make his theory easier to understand, Einstein compared often the time-space curvature to a rubber sheet which is being deformed by objects placed on its surface. Even today, the rubber sheet analogy is being used by scientists to visualize the gravitational fields of a massive object. What matters right now is to know that according to official science, Newton's theory correctly describes the gravitational interactions between objects at larger distances. However, if we want to properly describe the gravitational field in close proximity from its source, we need to use general relativity. Some of you might start to wonder how is it possible to get similar results from models which are based on completely different concepts of gravity and use completely different math. And the answer is because both models of gravity use something known as shell theorem, which was calculated by Newton himself and is crucial as for the subject discussed today. According to mainstream science, an important application of the law of gravity is showing that the net gravitational force on a mass m anywhere inside a uniform spherical shell of mass m is zero. Newton used then his calculations to state that since a uniform shell of matter exerts no gravitational force on a particle located inside it, we can conclude that a uniform spherical shell of matter attracts a particle that is outside of shell as if the shell mass were concentrated at its center. And then he decided to go even further and stated that since there is no gravity for a body placed inside an empty spherical shell, there won't be no gravity for a body placed inside a sphere which is filled uniformly with matter. And from such statement he was able to conclude that the force between two solid spherical masses or two shells of different radii is the same as the difference between two point masses separated by their centers. As this wouldn't be still enough, some other physicists went even further and concluded that the shell theorem can be also applied to other symmetrical shapes of 3D objects, like cube, tube, tetragon, torus, or trendy shape of flat disk. And now let me explain what are the implications of this unpretentious theory for the mainstream models of gravity. You see, because of the shell theorem, mainstream model of gravity is able to completely ignore the size and density of most celestial bodies and use only their mass to calculate their gravitational field. This is why every professional physicist will tell you that if our sun would become a black hole, it wouldn't have any effect on its gravity and the orbital motion of planets. Better, according to mainstream science, sun could turn into a cube or flat disk and it still wouldn't have any influence on orbits of planets, as everything with symmetry in its shape is treated as a dimensionless point of mass. And of course, shape of most spiral galaxies can be described as a disk with sphere in its center, what makes it symmetrical. And this means that if a giant hand of God would squeeze an entire galaxy to the size of a dust grain, external time-space curvature and magnitude of its gravitational field wouldn't change even a bit. How can it be that up until now only few scientists were able to see that there is something wrong with the famous shell theorem and its implications? And what could make them think so? Let's begin with a simple experiment which uses the famous rubber sheet analogy. All you need to do is to take two spherical objects with different sizes but the same mass and compare the way in which they curve the surface of rubber sheet. Next step is to see if objects with different sizes will attract other objects with the same strength at the same distance. Place a small sphere on the edge of rubber sheet, take a nail and some round object with a bigger radius and try pushing down the sheet until the distant object won't start to move. Compare how much force you need to use for both objects. And finally, take a hollow tube, place it vertically on the rubber sheet and simulate a change of its mass by pushing it down by hand. Look at the curvature of rubber sheet inside the tube. This is a simple visualization of gravity inside an empty spherical shell. First experiment should show you quite clearly that size of a sphere has significant influence on the curvature of rubber sheet. This simple drawing shows the difference of rubber sheet curvature for spheres with different sizes and similar masses. Bigger sphere creates a wide and shallow curvature, while a smaller and denser sphere curves the sheet stronger but at smaller area. You could probably say that I didn't discover anything new, and that all of this was pretty obvious from the beginning. You're right, for most of common people it is something obvious. But obviously not for professional physicists, who believe only in calculated numbers. And this is the result of my second experiment with rubber sheet. I think that this recording shows clearly that you need much less mass for a larger source to affect a distant object than for a point-like source, which if pushed hard enough might make a hole in the rubber sheet rather than increase the radius of curvature. As I said, it's all pretty obvious. And here is the result of my last experiment. You should be able to notice that the sheet under a hollow tube remains flat, no matter how strong we will keep pushing it, what means that object inside that tube won't be attracted to its edges. And here you can see how it can be translated into a representation of gravitational field inside an empty spherical shell. But here things become tricky, as such result would mean that Newton was actually right and there is no gravity inside a spherical shell. However, there is one problem with such experiment. You see, in this scenario, space outside and inside the shell remains connected by the rubber sheet. As the result, the stronger we will push the object down, the stronger the sheet will stretch to the sides. But in the official models of gravity, space inside and outside of a source is described by two different metrics derived from interior and exterior Schwarzschild solutions. In shortcut, to get a valid result, there can't be any connection between the rubber sheet within the object and beyond it. Sadly, I don't know how to make it happen. I know, however, an easy way to disprove the idea of zero gravity inside a spherical shell. All we need to do is to begin from two objects with equal mass and their gravitational influence on object which is placed exactly between them. It should be quite obvious that the test object will be attracted to both sources with the same strength, only it will remain exactly in the middle of the distance between them. In any other case, it will start moving to a closer source. And now let's simply duplicate this pair of sources and place them perpendicularly to the previous two. As the result, test object placed exactly between the sources is now being attracted with equal strength in four directions: left, right, up and down. And now let's continue duplicating the pairs of sources and placing them symmetrically around the test object in the center. Notice that despite the growing number of sources, we keep ending up with the same result, as long as test object is placed exactly in between. Finally, the number of sources surrounding our test object becomes so high that we can start treating them as a solid surface of a spherical shell. But could it be possible that at some point of this process, test objects stop to be attracted towards the sources which are surrounding it? And the answer is no. Test object will continue to be attracted by the sources no matter if we treat them as multiple objects or a single and solid surface of spherical shell. In the end, test object needs to remain being placed in the exact center of spherical shell, or it will start moving towards the closest point on the inner surface of that shell. And this means that inside an empty spherical shell, gravity is present and keeps attracting matter towards the inner surface of that shell. And now let's combine this knowledge with the official model of gravity, which requires the interior and exterior metrics to match each other at the boundary, which is placed at the surface of a gravity source. As a result, we should end up with something similar to this diagram, according to which matter is attracted to the surface of empty spherical shell with similar strength on both sides of boundary. Now the question is, how will it affect the official model of gravity? If you are smart enough, you should be able to guess already that the effects might be quite significant in the modeling of gravitational fields for the sources with small density of matter. Why? Well, maybe because matter is here attracted towards the surface of a sphere and not towards its center, what makes a huge difference for a large and less compact spherical body. Here is a simple comparison of gravitational field oriented towards the center of a sphere and one oriented towards its surface. Curvature is exactly the same in both cases. And this is probably the right moment to look at other cases of symmetrical geometry. Actually, I need to discuss only one more kind of 3D symmetry to deal with the problem of gravitational fields of galaxies. I mean, of course, the shape of uniform disk. Ladies and gentlemen, time has come to speak about the gravity of flat Earth. It wasn't easy to find any image which would show the orientation of potential field of a pancake Earth. This one comes from a movie from Vsauce channel, in which he discusses the general absurdity of flat Earth theory. As you can probably see, in the case of a thin uniform disk, orientation of gravitational field is directed towards the center of mass in flat Earth, placed at the very center of circular disk, exactly as in the case of uniform sphere symmetry. This means, of course, that physicists decided there is no real difference between spheres, disks, rings and donuts, and we can treat all of them as mass compressed into a dimensionless point in space. Simply put, If we will now translate all of this to the language of rubber sheet, I should be able to take a metal disc and a needle, and every time when the mass energy would be equal for both source objects, I would get exactly the same results. I could literally drop on the rubber sheet a 5 kg metal disc with 20 cm of diameter and get the same result while applying equal amount of force to the rubber sheet using nail and a hammer. I'm not joking. This is exactly what you will hear from 99% of educated physicists. There is no difference between spheres, rings or disks, as all such objects don't differ in fact from infinite small points of concentrated mass. Prepare for brick-penetrating pancakes and armor-piercing bullets splashing into pieces on a wooden plate. This is exactly where we get with the current model. We treat an inflated rubber inner tube just like we would treat a steel marble with equal mass. Don't you see a problem here? And now let's see how this extraordinary model describes gravity on the surface of a pancake Earth. As you could expect from a model with such innovative mechanics of gravitational fields of symmetrically shaped objects, according to its astonishing predictions, on surface of a giant cosmic uniform disk, every round object will be always continuously rolling and tumbling towards the exact center of disk. In such case, I have an idea for a very cool contest for physicists. Point is to demonstrate experimentally that a sphere placed on the flat surface of an uniform disk will roll towards its center of mass and geometry. Size and mass of objects don't matter. You can use a 200-ton disk made of steel and with a 20 meters of diameter, or you can use a coin. All you need to do is to prove experimentally the existence of gravitational attraction of a body towards the center of an uniform disk. It shouldn't be very difficult. Just show me couple spheres which will keep gathering in the center of a flat disk surface. Because I say that a sphere placed on the surface of flat and uniform disk will stay still in every point of that surface, except the edges of disk. Prove me that I'm wrong. Of course, it's not the first time when I challenge the entire scientific community and ask the physicists to show me that their models are in fact capable to give some valid results when applied to a couple of my simple scenarios. And of course, until today there wasn't no one who would accept my challenge and give me a proper solution. Maybe this time will be different. Last time, when I was discussing the subject of gravity on an internet scientific forum, I simply compared this simulation of gravitational fields to things that I observed while playing with the rubber sheet model. Of course, results predicted in the computer simulation didn't match the things observed on the rubber surface. As you probably can see, in the virtual simulation, size of a spherical source affects only the depth of gravity well and doesn't influence its radius. However, on the rubber sheet, size of the source has significant impact on both depth and radius of gravity well. This means that one of models doesn't work properly. Try to guess what was the response of forum scientists. Well, they simply told that the rubber sheet model is not a valid representation of a gravitational field because it works only in 3D and doesn't include dimension of time, so I can't treat its predictions as scientifically valid. Yes, I know that I don't need to operate on time to describe the geometry of gravity well, and that in 99% of all cases, things which can be directly measured are the correct ones. However, physicists seem to prefer playing with virtual numbers than observe the actual physical reality. It was for me an important lesson, thanks to which I learned that the only thing which can possibly convince a theoretical physicist is a mile-long string of mathematical calculations written down by some other theoretical physicist. and today I wouldn't try making any radical claim without any scientific publication as a support. Let's begin from a paper which discusses the problems of singularities inside hollow spheres, which emerged from the assumption that vectors in gravitational field of spheres are pointing towards their centers and not towards their surfaces. Author proves that singularities with infinite pressure in the center of a black hole is impossible. I won't go into the details, but it makes a closer look at the gravitational field of hollow sphere with a liquid with constant density and pressure intensity. Here's a fragment which states that singularity in the center of a spherical body can be avoided by placing the boundary between inner and external metric at the spherical surface. Here we can see an example of a hollow iron sphere with a very small inner bubble. Curvature at the center is zero, flat rubber sheet, so it can be infinite at the same time. And here we can see a very controversial conclusion. And I thought that my claims are radical. In the end, he is slightly more polite while pointing out a possible mistake in Einstein's general relativity, but keep in mind that author of this paper is a professional physicist, while questioning Einstein isn't very popular among the scientific society. It makes me happy that there are still physicists who are prepared to risk their careers for the greater good of science. But let's look at another paper. I think that the title of this publication speaks for itself. Also notice the date. It seems that for the first time science is one step ahead of me. Don't worry, I still have plenty to tell. And once more we can see that author is questioning the issue of spherical bodies being treated as points of mass located in the center of a spherical symmetry. And in the conclusion we can read that the gravitational field of bodies with spherical symmetry is not as entire mass of body concentrated in its center. And this is what I stated just a couple minutes earlier. And here's another paper which was published less than a year ago. It describes a new way to define gravitational fields of oblate spheroids, flattened spheres. Instead of treating those objects like points of mass, oblate spheroids are described as circular disks stacked in layers. Notice that the gradient of gravitational potential, image E, is not concentrated at center of the smallest disk on top, but is constant over its entire surface. And once again it is stated that force of gravitational attraction is not equal to the inverse square of distance despite the apparent field orientation towards the center of oblate spheroid. And those two images represent the gravitational field of an oblate spheroid, which is flat enough to represent a galaxy disk. In conclusion, authors explain that the problem of rotation curves of galaxies can be solved without virtual dark matter only by treating galaxies like flat spheroids instead of points in space. And finally, a paper published in 2016, which perfectly summarizes the subject of galaxy rotation curves and dark matter halos. Its title says everything. And once again, authors state that faster than expected rotational velocity of spiral galaxies comes from the fact that they are being treated as points of mass. According to their calculations, rotational velocity can be explained by treating the galaxy like a flat disk instead of dimensionless point. Once again, it turns out that it's possible to explain the rotational curves without any modifications of general mechanics of gravity model or without non-baryonic dark matter. All what is needed is to start including in the calculation shape and volume of symmetrical objects. Gravitational field of a galaxy can be the same as field of point source with equal mass. You don't have to be a genius to figure it out. I will end this part of the subject with a simple simulation of gravitational field which I made in my favorite 3D software. It appears that it has a built-in algorithm to simulate cloth and other materials. I created a disk of rubber sheet and dropped on its surface source objects with different shapes and sizes. Those are the results. And here's a comparison between disk-shaped source object and smaller spherical one. And this is where I will end today's lesson. In my next movie, I want to discuss another way to deal with the galaxy rotation curves, which has much less to do with gravity and much more with plasma physics. Class dismissed.